A young star in Orion, just 100,000 years old, is doing something the universe almost never lets us see. For the first time, astronomers have caught planets beginning to form in real time. This is breaking. Astronomers saw the birth of a solar system for the first time. Using the combined power of ALMA and the James Webb Space Telescope, scientists detected the very first spark. The inevitable moment when raw stardust hardens into the seeds of future worlds. If the birth of planets is no longer hidden, what else might be revealed about our own cosmic origins? The answer begins within this extraordinary stellar nursery. HOPS 315 sits in the L1630 molecular cloud, about 1,300 light-years from Earth, in a quieter corner of Orion. This star is astonishingly young, between 100,000 and 200,000 years old, still in its earliest phase of stellar evolution. At this stage, it hasn't yet reached the main sequence. Instead, it continues to gather mass from the surrounding gas and dust, its environment dense and turbulent. Most protostars at this age are shrouded by thick envelopes, but HOPS 315 stands apart. Its disk is tilted at an angle of roughly 40 degrees to our line of sight, a rare geometry that allows astronomers to peer directly into the inner disk. This orientation is not common. Often the outflowing jets from young stars block the view, hiding the regions where planets are born. In HOPS 315, the outflow cavities have carved natural windows through the dust, offering an unobstructed path for infrared and millimeter signals to escape. This unique vantage point became the focus of a major international research effort, led by Melissa McClure of Leiden Observatory. McClure's expertise in astrochemistry and planetary system formation placed her at the helm of a team determined to capture the first moments of planet birth. The group combined their strengths, coordinating observations across continents and wavelengths to take full advantage of this fleeting opportunity. The team's attention centered on the inner disk, a region corresponding to the area between Mars and Jupiter in our own solar system, where billions of years ago rocky planets and asteroids began to take shape. The surrounding disk of HOPS 315 is still thick with gas and dust, but the outflows have cleared enough of the envelope to allow a direct look at the warm, planet-forming zone. In most young stars, this region is hidden by dense material or lost in the glare of the star's jets. Here, the natural gap in the dust cloud combined with the disk's orientation revealed the disk's structure and chemistry with exceptional clarity. This rare configuration let researchers trace the earliest solid grains as they condensed out of the gas, a process that until now had only been inferred from the study of ancient meteorites and computer models. HOPS 315's youth means that the processes unfolding within its disk are happening on timescales measured in tens of thousands of years, a blink in cosmic terms. The material orbiting the star is still in the process of cooling, mixing, and settling. The star itself is on track to reach a mass similar to our Sun within the next million years, but for now, it remains a protostar, a cosmic infant surrounded by the raw ingredients of future planets. This makes HOPS 315 a natural laboratory for testing decades of theory about the origins of planetary systems. In this system, the earliest steps of planet formation are not a matter of speculation. They are visible, measurable, and unfolding in real time under the watchful eyes of McClure's team. At the heart of this investigation stand two of humanity's most advanced astronomical instruments, each built to pierce the cosmos in its own distinct way. The Atacama Large Millimeter/Submillimeter Array, or ALMA, stretches across the high plateau of Chile's Atacama Desert, more than 5,000 meters above sea level. Its network of 66 antennas functions as a single, massive eye, tuned to millimeter and submillimeter wavelengths. This range is critical for probing the coldest, densest regions of space, where dust and gas shroud young stars from visible light. ALMA's sensitivity at these wavelengths allows it to track the faint thermal emission from dust grains and to detect the spectral fingerprints of molecules like silicon monoxide, which can signal the earliest steps of planet formation. Yet, even ALMA faces limits. The densest parts of a protostellar disk, especially near a newborn star, can remain hidden behind curtains of dust that absorb and scatter millimeter waves. Here, the James Webb Space Telescope enters the story. Stationed at the Sun-Earth L2 point, nearly 1.5 million kilometers from Earth, JWST operates in the infrared, a domain that can slip through dust and reveal the warm, dynamic heart of a planetary nursery. Its instruments are capable of detecting the glow of the hot mineral grains and mapping their distribution in the inner disk, regions far closer to the star than ALMA alone can resolve. The synergy between these observatories is not simply additive. ALMA excels at mapping the cold outer layers and tracing molecular gases that mark the raw material for planet formation. It can separate the motion of gas in the disk from that in the jets, measuring velocities and pinpointing where specific molecules reside. JWST, by contrast, can look through the dust to the innermost regions, where temperatures soar and silicate grains first condense out of the gas. Its infrared spectrographs can identify the chemical composition of these grains and determine their temperature, providing direct evidence of mineral formation as it happens. This dual approach offers a complete, multi-layered view of a system like HOPS 315. ALMA's data reveal the structure and movement of the cooler, more distant disk material, while JWST exposes the hot, mineral-rich zone where rocky planets may begin. Together, they allow astronomers to connect the chemistry of planet building to the physical processes shaping the disk. The ability to combine high-resolution maps of gas and dust with detailed infrared spectra is what makes it possible to catch the very first moments of planet formation, moments that would remain invisible to any single instrument. In this coordinated campaign, ALMA and JWST are not just complementary, they are interdependent. Each fills the observational gaps left by the other, creating a unified vision of a process that unfolds over thousands of years and across billions of kilometers. It is this collaboration that transforms a fleeting glimpse into a comprehensive record of planetary genesis, setting the stage for the evidence that follows. ALMA's millimeter wave array detected a sharp signature of silicon monoxide gas swirling in a tight ring no farther than 2 astronomical units from HOPS 315. This region, heated to over 1200 Kelvin, matches the temperature where silicate minerals first condense out of the gas. The velocity structure of the silicon monoxide emission, measured with a precision of just a few kilometers per second, revealed orbital motion consistent with material circling in the disk, not racing outward in protostellar jets. By analyzing the Doppler shift across the disk, astronomers confirmed that the gas was moving at speeds expected for a radius analogous to the asteroid belt in our own solar system. At the same time, JWST's infrared spectrographs pierced the dusty envelope and recorded the distinct absorption lines of hot crystalline silicates. These grains, forming in the same inner region, produced a spectral fingerprint identical to laboratory samples of forsterite and enstatite, the first solids to appear as a solar system cools. The spectral line shapes depended on their distance from the star, and the best fit placed them within the same 2 astronomical unit zone mapped by ALMA. The temperature of these grains, measured at over 1200 Kelvin, confirmed the minerals were freshly condensed, not relics from an earlier epoch. The alignment of spatial, thermal, and kinematic data from both observatories clinched the case. The silicon monoxide gas and the crystalline silicate grains are co-located, caught in the act of transforming from vapor to solid. This real-time convergence leaves no doubt. The first building blocks of planets are solidifying now in full view within the disk of HOPS 315. Calcium aluminum-rich inclusions, or CAIS, are among the oldest solid materials in our solar system, preserved in meteorites like Allende. Their presence records the very first moments when dust grains solidified from hot gas billions of years ago. The same process is now being traced not through ancient samples, but as it unfolds around HOPS 315. This connection between distant starlight and meteorite fragments on Earth closes a loop long theorized but never directly observed. The minerals condensing in HOPS 315's disk echo those found in chondrites, linking our origins to the present-day birth of new worlds. For planetary scientists, this is more than a technical milestone. It's a living record of the conditions that once shaped our own planet, captured not in stone, but in light. Fred Chiesler, a planetary scientist at the University of Chicago, puts it plainly. Astronomers have been thinking about how planetary systems form for a long period of time. This is one of the things we've been waiting for. The ability to watch these grains solidify in the very region where asteroid parent bodies formed in our solar system offers a testbed for every model of planetary birth. The next steps are clear. Continued monitoring of HOPS 315 will track the evolution from hot grains to planetesimals, revealing how quickly solids grow and migrate. Researchers also plan to search for other protostars at this stage, to learn if such mineral formation is a universal step or a cosmic rarity. Each observation refines our understanding of how planetary systems like ours come to be and whether the story told by meteorites on Earth is written throughout the galaxy. In 2025, astronomers confirmed a first: direct evidence of planet-building minerals forming around the protostar HOPS 315, just 100,000 to 200,000 years old and 1,300 light-years away. Using ALMA and the James Webb Space Telescope, the team identified silicon monoxide gas and crystalline silicates, the earliest solid grains, within the disk. This marked the earliest observed stage of planet formation outside our solar system, matching the process seen in ancient meteorites from Earth. While the data reveal the presence and location of these newborn solids, questions remain about how quickly they will grow into full planets, and whether similar events are common throughout the galaxy. Ongoing monitoring and comparison with other systems will be needed to answer those questions. Today, scientists have captured the time zero of planet formation, a factual, documented moment that brings us closer to understanding how worlds like ours can arise.